Fossil fuels have been the backbone of our society's survival for centuries. However, it's time to transition to alternatives due to depleting reserves, long-term effects on ecology, and even political disputes. With this, one of the most promising avenues for renewable energy generation is through photovoltaic technologies. As of the moment, 80 to 90% of the current solar panel market share is comprised of crystalline silicon. It might be abundant, but it requires resource-demanding and heat-intensive manufacturing processes. To add, it is limited by its indirect bandgap, requiring thicker sheets of it to be made. With fully inorganic perovskites at the front line of replacing these conventional solar cells, it promises an immense growth rate compared to its predecessors, especially with its direct bandgap, high light absorption coefficient, and a much simpler and sustainable laboratory synthesis. Alpha-cesium-lead iodide stands as one of the most studied perovskite candidates for photovoltaics. To further the research on this material, doping through substitution is utilized to produce different halide combinations on its X site. This generates relatively novel studies on three materials. At the nanoscale, the complexity of interactions within them is described by the many-body problem. Using density functional theory, the Hamiltonian is reduced to non-interacting one-electron Schrödinger-like equations, enhancing computational efficiency in describing these semiconductors. If results demonstrate their viability as photovoltaic candidates, then that's great. But if they fall short, the findings could save time and resources in laboratory experimentation and even mass production.